Hello, I'm Charlie Bryant, and this is Lab 5, in which I choose to investigate projectile motion. The objectives are, firstly, to analyze the motion of a 2D projectile and computationally deduce the angle to the horizontal at which the object was initially launched. Then we'll create a model of that motion. Then we're going to analytically and computationally deduce the angle with the horizon that will result in the maximum displacement in the x direction. The fundamental physics principles involved are Newton's second law. So the change in velocity is equal to the net force times the mass of the object over the change in time on which the force acted on the object. Our results were that the predicted range and actual range recorded in the x direction differed by about 5 centimeters. Let's explore that further. Here's the analysis of a wiffle ball toss using tracker. I set my axes so that the positive x direction is towards the top of the screen and the positive y direction is to the left of the screen. Looking on the right side, you can see that the x component of the velocity appears about constant, whereas the y velocity is parabolic. To find those initial velocities, I looked at our data points at the table you can see on the right side of your screen. The initial x and y component were found using our data and tracker and then dividing by the time step. To find the magnitude of the velocity, I then squared each of those components and took the square root. The initial velocity's magnitude ended up being 4.36 meters per second. Then using those components, I wanted to find the angle theta at which the ball was thrown. Some quick trig shows us that the tangent of theta is equal to the y component of the velocity divided by the x component of the velocity. So then solving for theta, we find that it was thrown at about 45 degrees. Now onto the model itself. I set the initial conditions for the weight to be 0.045 kilograms, which I found online to be the weight of a wiffle ball, the speed we just found, and the position I set to be the origin. The velocity, the x component, is the cosine theta of the speed, and the y component is the sine theta of the speed. And I had 3 different thetas, being 30 degrees, the angle we just found for our theta, and then 60 degrees. For the model itself, it was assumed that the net force was only the weight force in the negative y direction. Then we implemented Newton's second law to update the velocity. Lastly, the position was updated using that new velocity times our time step. I'll now run the model. You'll see 3 balls being thrown, the first one at 30 degrees, the second one at 60 degrees to the horizon, and the last one at the angle we found, which was 45.2. Notice how that last one went farther than the first 2. So what does it mean that a discrepancy exists between the model and what we actually found using tracker? In short, it means that there are external forces acting upon the wiffle ball that we didn't account for in the model, notably the drag force. With the drag force will continually push a ball in against the ball in the x direction, so the x component of the velocity is not constant. So how can we find the angle of maximum horizontal displacement? There are 2 options. 1, using calculus, and 2, iteratively seeking the maximum using VPython. We'll try both. Let's use calculus to show what the angle of max x displacement would be. The formula for x displacement in 2D projectile motion is that delta x is equal to the initial velocity squared times the sine of 2 theta, the angle at which it was thrown, divided by the acceleration due to gravity. So taking the derivative of that with respect to theta, we get the initial velocity squared over the acceleration due to gravity times 2 cosine of 2 theta. Now we'll set that equal to 0 to try to find a max for theta. This term cancels out, and we're left with cosine of 2 theta is equal to 0. So when cosine is equal to 0 is when it's at 90 degrees. So we find 2 theta is 90 degrees, and so theta is 45 degrees. Here's how I computationally found the maximum x displacement. The code from the previous model was nested inside another while loop that iterates through tossing the ball with every angle starting from theta equals 0 until theta is up to 90 degrees. Theta is then incremented by half a degree in between every toss. The distance the ball was thrown in the x direction, as well as the angle it was thrown at, are then appended to a list, and then the program prints out the maximum distance that the ball was thrown and the angle associated with it. I'll now run the model. I know that this could be even more accurate if our step in our angle and our step in our time were even smaller, but due to computational restraints, we could not make those angles smaller. And as you see, it prints out the maximum distance, and the angle at which it was thrown was indeed 45 degrees. So what if we examine projectile motion on a different planet? Would the angle for the maximum x displacement be the same? In short, yes. The angle would still be 45 degrees, because going back to our calculus analysis, maximizing theta was independent of the acceleration due to gravity. So even if the g changed for accounting for a different planet, the angle would still be the same.